All right, we're going to actually take a little bit more time and look into intermolecular forces. We're actually going to split this out into a separate section. Originally, it was a part of section 2, but we want to take a little bit of time, and now we're going to actually do some comparisons between what we call intermolecular forces and the intramolecular forces, the bonding forces that we talked about in the previous section. So let's go ahead and get it started. Now, what is an intermolecular force? Intermolecular forces are the attractions that we see between molecules. They're usually going to be based on the type of bond that's formed and the polarity of the bond that's formed. If there is no polarity, if it's not a nonpolar compound, we usually see less of intermolecular force or less attractions between the molecule as we would see for those that are highly polar in their nature. Now, the first type of bond that we're going to look at here is we're going to look at dipole-dipole interactions. Now, we talked about before a dipole being and two atoms, or sorry, having two different charges on one compound, usually shown to us by that strange symbol. It looks like this, slightly positive, slightly negative. Now, this is going to show us, or how we'll be able to find this is we look at the polar bonds reacting to electric fields, or looking at how they interact overall. Now, these type of compounds are going to form what's called, or exhibit what we call, a dipole moment. Usually it's going to be tracked looking at dipole, which is the units. Don't worry about those. We'll talk about that later though. Now, this is basically talking about the attraction between these slightly negative and slightly positive sides, where the molecules will line up according to opposite charges, like slightly negative, again, with the slightly positive. Now, for intermolecular forces, I want you to understand that these are going to be very, very weak interactions. So for a dipole-dipole interaction, we're looking at about 1% or even a little bit less the strength of a normal covalent bond. Now, this is going to help us to understand that this is going to occur, but these are not anything set in stone in terms of interactions that we broken and formed very quickly. Now, this is a diagram showing you what's happening in a dipole-dipole situation or interaction. You notice that we're starting to see the negative and the positive sides being attracted. Along with this, because it doesn't form into one long line as we would normally think, we're also going to have a little bit of a repulsion. The negative and negative ends, positive and positive ends will try to repel each other. But depending on how they orient themselves, we'll be able to see how those interactions will be involved in the actual formation of these different compounds, how it affects things like boiling point, melting point, and so forth as we go throughout the year. Now, the second type of intermolecular force we're going to deal with is the hydrogen bonding. Now, this is going to be the strongest of all of our intermolecular forces. We only talk about three, but this is going to be the strongest one. Now, this is what's responsible for what we call surface tension in water. We're going to end up with a similar type of dipole scenario, but it's going to be involved with the hydrogen of one compound being attracted to the highly electronegative atom of another compound. Notice again, for hydrogen bonding, it's hydrogen of one compound being attracted to the highly electronegative atom of another one, so like oxygen or fluorine or something along those lines. Now, when we look at the hydrogen bonding, those that exhibit hydrogen bonding are usually going to have much higher boiling points for two main reasons. One, the large electronegativity values between the highest elements in the group. Remember, we talked about the trends and the highest values being at the top. And the second, the smaller size due to lack of electron rings will actually allow the elements or the atoms to interact a lot closer. This is going to end up with a stronger intermolecular force. Let's look at a diagram to make this a little bit clearer. Now, if we're looking at our first three here, we have water, and then we're going to see a drastic drop here when we deal with hydrogen sulfide, hydrogen selenide, and hydrogen telluride. But they still never reach the point of what we have here. Same with fluorine, we're going to see a drop, but then a sudden increase. And ammonia here, we're going to decrease, and then it begins to climb, and it actually gets very close to, if not a little bit higher. Now, the question is why? Because especially as we look at methane here, and as we look at, sorry, our stibium hydride, so antimony hydride, we're seeing that they actually get up to or go higher than the element in that first situation. Well, what we're dealing with here is now we're dealing with tin, germanium. These are actually metals. Antimony, also a metal. So we go from dealing with covalent compounds to, in our fourth period, which is what we have here at the bottom, we're dealing with ionic compounds. This is going to have a much, much higher boiling point than our non-metal would be. Why? Because you have to go all the way through and break that electrostatic interaction in order for it to actually occur. Now, we're going to continue looking at this as we move forward, but I just want you to pay attention and see how these sort of interact, or how they sort of play out in terms of our energy and our periodic trends. Now, our last and final intermolecular force that we're going to deal with here is called a London dispersion force, or LDF. Many times you'll hear it say. Now, these are the ones that are going to occur between nonpolar molecules. Now, if you're saying in your head, okay, nonpolar molecules, why are they going to interact? How are they going to interact? We're actually going to look at the fact that it's due to random electron movement. That's going to cause what we call an instantaneous dipole. So we have the electrons, as you see in the diagram here. We have these two nonpolar molecules and the electrons that are around them. Now, electrons are very unpredictable in their movement. That being the case, sometimes you'll have a large group on the left, and sometimes you have a larger group on the right, and they continually move around as they wish. Now, as we look at how this is, originally we have nonpolar, no polarization possible or happening. But as those electrons shift away, now I have this slightly negative side and slightly positive side. When the opposite happens to the other side, I'm actually going to get these where they form a little bit of a attraction. And this is going to be very, very quick and very, very brief, very, very weak, sorry. It's going to be the weakest of all our intermolecular forces. Now, the larger the compound is, the more chance you're going to have your London dispersion forces. So the larger we have with our hydrocarbons, we'll talk about, is usually going to cause them to stick together and be more viscous. So if you've ever heard of the word viscosity, usually dealing with the resistance to flow or how thick something is, like with oil or wax, this is where we're actually going to see an increase in viscosity. We'll keep that going for later though. Now, at this point, we're going to go ahead and move into our actual thermochemistry chapter. This is going to be the information from chapter 6 in the textbook. We're giving you all the background. Now we're going to see how it affects our actual reactions. But we'll do that in the next video. Write down your questions. I'll see you in class and can't wait to hear them. Have a good evening.